Hello dear students, welcome to the channel and welcome to this playlist in which we are discussing 8051 microcontroller. Up until now we have discussed about basics of 8051, we have discussed about the architectural block diagram, we have discussed about the pin diagram, we have discussed about different pins of 8051 microcontroller. We have also discussed about the serial input output ports and four external ports of 8051 in general. And today we are going to discuss about the timers and counters in 8051. Basically we are picking up right where from we left in the previous class. So if you haven't checked out previous videos, the link will be flashing on the top right hand side corner of your screen, so you can click on it and follow it. Now coming back to the timers and counters. So 8051 has 16-bit timer counter registers, two in total, which are named timer 0 and timer 1. And we can independently configure both of these registers by in order to operate as a timer on an event counter. Now when used as a timer, the register is programmed to count the internal clock pulse. So the internal clock pulses are generated from the constant clock generator, and the count loaded in the register will give the constant time. So the register is incremented at every machine cycle, and once machine cycle consists of 12 oscillation periods, so the counting rate would be 1 by 12 of the oscillation frequency. So when used as a counter, the microcontroller is programmed to count external pulses, and the register is incremented in response to the high or high to low transition. And high to low transition of what? So transition of corresponding external input pin, right? Whether it T0 or T1. So this external input does not have the constant frequency, and because of that it is not used for timing reference. So in order to recognize the high low transition of microcontroller, you require two machine cycles, right? Which means 24 oscillation periods, because one machine cycles consist of 12. So what will be the counter rate this time? It will be 1 by 24, right? 1 by 24 oscillation frequency. So the counter or timer registers, which are divided into 8-bit registers, are known as timer low, which include TL0 and TL1, and timer high, which include TH0 and TH1. Now this TL0 and TH0 combinedly forms a 16-bit timer 0, and TH0 and TH1 sorry TL1 and TH1 forms a 16-bit timer 1. Now the counter action is controlled by the bits in the timer mode, which is known as timer mode control register, or T mode, and the timer counter control register is known as TCON, right? So timer mode control register will be T mode, and timer counter control register is called TCON. Now let's come to this image. So you would be able to see the gate pulse, which is controlling the pulse given to the timer. This CT that you are seeing here for the timer 1, so it will select the counter operation of my timer operation, and CT bar 0 will stand for timer, and CT bar 1 will stand for the counter, right? So the basically mode bits are going to select different modes of operation of the timer. Simple. Now this is for timer 1 and this is for timer 0. So MSB bits are for timer 1 and LSB bits are for timer 0, least significant bit and most significant bit, MSB and LSB. So why do we use the gate? So we use gate control when we set the gate control as a timer or counter X, and when we enable it only while interrupt X or INT X pin is high and TRX pin is set, then we clear the timer X and it will be enabled whenever TRX control bit will be set. Similarly, the counter selection, timer or counter selection. So when we cleared for the timer operation input from internal system clock, we set for the counter operation, which would be input from TX input pin, right? Input from TX input pin. Now for different values of M1 and M0, we will be getting different operating modes. So when M1 and M0 both of them are 0, we will be getting 8-bit timer counter THX with TLX as 5-bit prescaler. When M1 will be 0 and M0 will be 1, we will get 16-bit timer counter THX and TLX, both are cascaded and there would be no prescaler. See, earlier we are using TLX as a 5-bit prescaler. When M0 becomes 1, we are not considering as a prescaler, we are cascading them. Now when M1 would be 1 and M0 would be 0, we will have 8-bit auto reload timer counter. So THX will hold a value which is to be reloaded into TLX each time it overflows, right? And whenever we have M1 and M0 both 1, for timer 0, the TL0 is a 8-bit timer counter which is controlled by the standard timer 0 control bits, and TS0 is 8-bit timer only controlled by the timer 1 control bits. But for timer 1, the timer or counter could be stopped at M1 equal to 1 and M0 equal to 1. Now, wait a minute, I accidentally changed the slide. So, see, the gate is controlling the pulses given to timer, and CT is performing the same thing as we saw or discussed earlier. Now let's see the mode control registers. Before we go to the mode control registers, let's see the basics, because basically this was the mode control register, but let's see each register one by one. So moving from MSB to LSB, the first one you are seeing here is TF1, this one. The position of this in the pin diagram would be the TCON7 position, and what significant it holds. So TF1 is the timer 1 overflow flag, which is set by hardware on timer counter overflow and cleared by hardware when processor vector is interrupt routine, right? Processor vector to interrupt routine. After that, for the same in same order, moving further, we have TR1. So the position of TR1 would be TCON6 on the pin diagram, and this is also for timer 1. So timer 1 run control bit, and it will set or clear by the software to turn the timer or counter either on or off, right? Then we have TF0. The position of this one is TCON5 in the pin diagram, and this is, as you can see, it is from 0th TM0 0 timer. So the timer, this is simply timer 0 overflow flag. When you see F, it would mean overflow, and when you see R, it would be run control. So this is timer 0 overflow flag, which is set by hardware on timer counter overflow and cleared by hardware when processor vector to interrupt routine. Simple. Similarly, now you can guess the operation of TR0, but first let me tell you it is called TCON4 on the pin diagram, and timer 0 runs control bits. It would set or clear by the software to turn the timer or counter on and off. Similar operation it would perform. Then we have something interesting, IE1. The position of this command on the pin diagram would be TCON3, and it is an interrupt. right? Interrupt 1. So this is interrupt 1 edge flag, which is set by hardware when external interrupt edge is detected, and it is cleared when interrupt is processed. Then we have IT1. The position of IT1 in pin diagram would be TCON2, and it is interrupt 1 type control bit. So it will again set or cleared by the software to specify falling edge uh, or low level triggered external interrupts. Similarly, we have IE0, which is again TCON1 in the pin diagram, and this is for the zeroth pin, one more time, or zero timer, sorry, not zero pin, zero timer. So this is interrupt 0 edge flag, which is set by hardware when external interrupt edge detected, and it is cleared when interrupt is processed. Now similarly, you all can guess that IT0. So the pin diagram its position is TCON0, and I want answers from you guys. Please mention what would be the function of IT0 in the comments below, right? So that I can understand that you are following what we are learning in the class. Okay, so now moving towards the operations of timers, or shall I call it the modes of operation of the timer. So depending on the mode control bit M1 and M0 in the timer or counter mode control, which would be mean T mode control register, can update it in any of the four modes: M0, M1, M2, and M3. Or you can also call it mode 0, mode 1, mode 2, and mode 3. So now first let's see M0 or mode 0. So what happens in this mode, that the timer will operate as a 13-bit register, right? Again, as we discussed, the TL would have 5 bits prescaler and TH would have 8 bits. Remember, we discussed it over here. Let me show you here. See, THX with 8-bit THX with TLX as 5-bit prescaler. So that's what happening here. So the 5 bit in the TL set will be set, the 5 bits in the TL set sets the divide by 32 prescaler to TH as 8-bit counter, and the timer is enabled when TR would be 1, when gate would be 0, and INTX would be 1. So you can see the value of all of them: gate, INTX, and TR, right? And only after that the timer is controlled by the external input INT to allow the pulse width measurement, right? So TR is a control bit in the TCON register, right? So let me repeat it one more time. For the operating condition, TR must be 1, gate must be 0, and INTX should be 1. Now using as an interrupt, so if the user desires some count in the register and gives command by TRX bit, the timer or counter will start. And if the timer counter exceeds 13 bit, which would be FFFH, so the next count will be 000H, right? So the next count will be, sorry, no, not 000, it should be 4 zeros, I think, right? It would be 40H, and it will cause the microcontroller to generate the interrupt in order to inform the programmer whenever one cycle is over. So to indicate it, the time overflow bit will be set, right? Which means TF1 and TF0 will be set. See, following this, TF1 and TF0 will be set. So if the timer interrupt is enabled using the interrupt enable register, the control will vector to ISR routine. Now moving to from mode 0 to mode 1, what will happen? So in mode 1 of a timer or counter, the operation would be same as mode 0. See this figure and see this figure. You would see most of the operations same, except we are having different TL and TH values. So if you remember it from here, you can see we have 16-bit timer counter. THX and TLX are cascaded without prescaler. So TLX and TH both are cascaded. So the only difference between mode 0 and mode 1 is the mode Z. In mode 0, the timer counter was 13-bit timer counter, but in mode 1 we have 16-bit timer counter. Okay. Now moving to mode 2. Apologies, I think we skipped the mode 1. Sorry, this is mode 2. This is not mode 2. This is mode 0, and mode 1 looks the same, except instead of 13-bit, here we have 8 plus 8. Right, it would have 16, and this is the mode 2. So it is again configured as an 8-bit counter TL with auto reload facility. So here we have the auto reload facility, which is new here, and TL1 acts as the basic timer or counter, and when the timer starts working, it will overflow. So this will set the timer interrupt flag TF1, and it will also reloads the content of TH1 to TL1, right, from TH1 to TL1. And this reloading operation will not alter the contents of TH1. Okay. And the this 1 by 12 oscillation frequency that you are seeing here as well, right, C by T ratio. Then we have mode 3, the final mode. So in mode 3 we don't use the timer 1, so simply it would hold its count, and timer 0 registers TL0 and TH0 are configured to two separate bit counters, right, two separate 8-bit counters to be precise. So TL0 registers are uses the timer 0 control bits, C by T, gate, TR0, interrupt 0, TF0 and TS0 counts, right. So all of them will collectively will count the machine cycles, and it takes over the use of the TR1 and TF1 from the timer 1, right. So we will have something different, and whenever the timer 0 is in the mode 3, the timer 1 may be used in mode 0 or 1 or even 2, right. So you can use a timer in mode 0, 1 and 2 and in this case no interrupt will be generated because timer 0 is using the TF1 flag, and when the timer 0 is in mode 3, the timer 1 can be used as a baud generator from serial port, right. You can use the timer 0 sorry we can use the timer 1 as a baud rate generator for my serial port. So now if we are generating baud rate for serial port, let's discuss something about serial data or serial ports. So why do we use the serial ports? The first question. So for the communication between two computer systems, we need to send and receive the data, right. And how do we do it? We do it serially. So we send the data and receive the data serially. And this microcontroller 8051 has a serial data communication circuit, which is using the registers in the SFR called SBUF to hold the data. The register SCON controls the data communication, the register PCON controls the data rates, and the SBUF register comprises of two registers. So physically one of them is write only and is used to hold the data that is to be transmitted out from the microcontroller via TX0 pin, while the other one is read only data and will hold the data that is received from the external source via RxD pins. Now a full duplex asynchronous serial interface can be implemented on using serial interface control circuitry, and a double buff receiver is used in the circuit so that the receiver can receive a second character when the first one is an intermediate register. So double buffering will reduce the chances of an overrun error, what is called overrun error, and it will also reduce the chances of complexity. So the serial interface can be operated in total 4 different modes, again M0, M1, M2, M3, or mode 0, mode 1, mode 2, mode 3, and these modes can be configured using SCON, which is a serial port control status register. And how do these 4 modes behave? So mode 0 behaves as a shift register, mode 1 is 8-bit UART, mode 2 is 9-bit UART with fixed baud rate, and mode 3 is 9-bit UART with variable baud rate. And SM0 SM1 has specifically the serial port modes, specify the serial port modes as shown in the table here. With mode 0 we will have SM0 and SM1 both 0. It would work as shift register. The baud rate would be FOC by 12, the general or the common. When we use it as a 8-bit UART in mode 1, we have SM0 is 0, SM1 is equals to 1, and the baud rate would be variable. When we use SM0 as 1 and SM1 as 0, so we will enter into mode 2, we have 9-bit UART, and baud rate would be FOC divided by 64 or FOC divided by 32. And in the third mode, when both of SM0 and SM1 are 1, it would be 9-bit UART with a variable baud rate, right? So that was SM0 and SM1, but what SM2 will do? So SM2 enables a microprocessor communication feature in the modes 2 and 3, and in mode 2 or 3, if SM2 is set to 1, then RI will not be activated if the received ninth data bit RB8 is 0. And in mode 1, if SM2 is equals to 1, then RI will not be activated if a valid stop bit was not received, right? And in mode 2, SM2 should be 0. Then we have REN, which enables the serial reception, and it is set by software to enable the reception and cleared by software to disable the reception. Simple. So basically you don't play with the REN pin. Then we have TB8, which is the ninth data, which is the ninth data. It will be transmitted into modes 2 and 3, and it's set or cleared by the software as the software desires. So again, you don't mess with TB8 either. We have RB8. So in mode 2 and 3, RB8 is the ninth data bit that was received, and in mode 1, if SM2 is equals to 0, RB8 is the stop bit that was received, and in mode 0, RB8 is not used. Then we have TI and RI. So TI is transmitted interrupt flag, which is set by hardware at the end of 8th bit transmit in mode 0, or at the beginning of the stop bit in the other modes. Now in any serial transmission, it must be cleared by the software. Similarly, RI is the receive interrupt flag, which is set by hardware at the end of 8th bit time in mode 0, or halfway through the stop bit time in the other modes. And in any serial reception, it must be cleared by the software, right? Except of course saying SM2. Okay. So the modes 2 and 3 have a special provision for multiprocessor communication. Like we have the master slave configuration. It is similar to master slave configuration. Then we have the baud rate for the serial mode can be adjusted, so it is adjustable, and the clock source required for setting this baud rate is provided on the chip. So The baud rate would be fixed for mode 0 while it is variable for mode 1, 2, 3, and variable baud rates are determined by the timer 1 overflow rate. Then let me change the slide. Then we have the mode 0, detailed discussion about mode 0, not too detailed though. So this is half duplex mode, which refers as a shift register, and shift register has shift left, shift right operations. So the shifting operation of data bits is sequentially done, and the input to the shift register is data and clock. So the serial data is transmitted and received through RxD line, and the clock is generated by the TXD line. Now as 8 bit are transmitted at a time, the start and stop bits are not required. So the LSB of the data is transmitted and received first, and the baud rate for mode 0 will be oscillation frequency by 12, right? Simple. So the microcontroller chip has limited number of input output lines available, and in order to increase the input output lines, you can provide external input output chips like the shift register, and that is what it is for. Then we have the mode 1. Again, this is full duplex mode, and it will also support the 8-bit asynchronous communication. So whenever there is a change in the data 1, and whenever it is transmitted, so whenever there is a change in data, 1 would be transmitted and otherwise 0 would be transmitted. But although data bits are 8 bit, the number of transmitted bit are 10, which means one start bit, one stop bit, and then 8 data bits. So whenever a character is serially transmitting uh, the character is serially transmitted, the transmitting and receiving device should satisfy the communication protocol. So here, as you can see, in one frame we have one start bit initially and one stop bit at the end, and then we have 8 data bits. So the baud rate for mode 1 would be variable. The baud rate is determined by the time 1 overflow rate, which is typically timer 1 is used in mode 2, and as an auto reload 8-bit timer. The baud rate would be 2 raised to s mode divided by 32. So s mode is a control bit in the pcon register, so it cannot be 0 or 1. And if timer 1 is not in the mode 2, then baud rate would be 2 raised to s mode divided by 32 into timer 1 overflow rate. Now let me show you the table here. As you can see, this table is showing commonly used baud rates and why in which uh, showing you the commonly used baud rates and the way in which they can be obtained from timer 1. The oscillator frequency will be specified as well. So the baud rate mode 0 would be maximum 1 megahertz frequency. The oscillation frequency would be 12 megahertz. Given that, the S mode will be cross or none, and in timer mode everything would be none. Similar way for mode 1 and 3, maximum frequency is 16.5 k. So oscillation frequency again 12 megahertz, and S mode would be 1. And in timers we would have a reload value FFH, and mode would be 2, but CIT would still be 0. For mode 2 maximum we would have 375 kilohertz, oscillation frequency again 12 megahertz. We will have S mode 1, and again timer modes, all of them are cross or nothing. For 9.6 and 19.6 kilohertz, for value of S mode 0 and 1, you can see other values for like reload value, mode, CIT, and oscillation frequency here. And we have different values for different baud rates from 9.6 to 4.8, 1.4 to 1.2, all this in kilohertz, and after that 110 hertz. Right, we have till 110 hertz. So now let's quickly move to mode 2. So basically this mode 2 supports full duplex transition, and it supports 11-bit asynchronous communication. So whenever there is a change in data, again 1 would be transmitted and otherwise 0 would be transmitted. And such an operation is known as non-return to 0 and NRZ operation. So in this mode, number of the transmission bits are 11, which means one start bit, 9 data bits, and one stop bit. Okay, here we had one start bit, 8 data bits, one stop bit in mode 0, but in mode 2 we have one start bit, 9 data bits, and then one stop bit. Okay, so uh, ninth data bit is copied from the TB8 bit in the SCON register, and it is stored in the RB8 bit of SCON when data is received. So the start and stop bits are discarded. And again, baud rate, what would be the baud rate? 2 raised to s mod divided by 60 into oscillation frequency, because remember baud rate in this case would be variable. So in comparison to mode 0, the baud rate in mode 2 would be higher than the standard communication rates. And why is it so? Because the multiprocessor system demands high data rates, and that's why mode 2 is higher. And this mode is mainly used for microprocessor communication, or what what do I mean by microprocessor communication? So it means that n number of microcontroller based systems are interfaced to each other through a serial communication channel, and this will help to transfer the data from one system to another. So you can think of it like a WAN or LAN network. So it's more like a LAN network, right? It's something like a LAN network. Then we have mode 3. So mode 3 is nothing special, it is similar to mode 2, except that in mode 3 the baud rate is determined as in mode 1 using the timer 1, right? So there is a difference of timer only, except that mode 3 is totally similar to mode 2, right? Only changes the determination of baud rate. We used to use the timer 0, here we are using timer 1. That is the only difference here. So that would be wrap the ongoing chapter, and we will discuss more topics in upcoming chapters. So if you have any doubts or queries, please feel free to mention them in the comment section below. So I will try to answer them as many as possible, as soon as possible. If you have any suggestions for me for videos or even shorts, please mention them in the comment section below as well. If you have any feedback related to channel, whether it is positive or negative, please mention that as well, so that I can learn where this channel is going and what type of content that my subscribers prefer. So we will wrap this class here. Stay tuned for upcoming microcontroller lectures, and please ask doubts if you have so thank you very much for listening. I will be seeing you next time in the next class. Till then, thank you very much for listening, and goodbye for now.